Hi guys. Today we're going to be talking a little bit about graphing and rate of change and some of the relationships that exist in nature as far as if we were to mathematically interpret them. So we'll get into some of that stuff later on. So let's just begin with the idea of change. What is change? Things are always changing, right? And in earth science, we always define change as some type of alteration that happens within the environment. And there's lots of different examples of that. Change can be very instant. In other words, it happens like that, right? In 1 second, it was one way, and another second, it was another way. Or even within a matter of minutes or hours, change can be pretty quick. Things can happen in nature, and you can think about some changes in your mind that are very instant. Or you can have changes over a long period of time, maybe something that you don't even notice that it's changing. And that's very true with a lot of things on Earth as well. So just realize that any alteration of the environment is change, and we can measure that change in something that's called the rate of change. And we'll take a look at that in a second. So what are the two types of changes besides quick and long term? There's two different types, and the one type, and you can kind of see this in the pictures that are shown here, we have a change of the moon phases over a period of a month. And you can also see here the change in the foliage on a tree over the period of a year. So these types of changes are called cyclical changes or cyclic changes, things that are going to repeat themselves over and over and over and over again in a predictable way. We can make predictions about when the next full moon will occur. Or we can make predictions that the trees will start to change the color of their leaves in the fall. Because why? Well, it's been happening that way forever, as far back as we can remember and as far back as we've recorded. So things that are predictable are cyclical. Okay? There's also some changes that are not predictable, like a lightning strike or an earthquake, things that happen pretty quickly and we have no way of telling when they're going to happen or when they're going to change the environment. So these are called non-cyclic changes, things that don't repeat themselves in any regular pattern, that are not very predictable. Now they are working on the idea of predicting earthquakes, but they haven't gotten there yet. We can't really say exactly at what moment in time an earthquake is going to happen. And the same is true with lightning. Okay, so the idea is there are cyclical changes, or predictable ones, and non-predictable ones. Okay, now we in science deal with an equation called the rate of change. This is essentially just how fast or how slow something is changing over time. And we'll maybe do some math with this, but the equation for this is right on your reference table. And remember, you're going to be receiving, or you received a copy of the reference table already, and you'll see that the equation for rate of change is right there in the equation box, rate of change. Okay? Now, the rate of change formula is change in some type of value over time. So the time is on the bottom in the denominator, and we have something changing in the numerator here. And remember, when we're dealing with change mathematically, we're talking about subtracting two values here. We have something at the very end, and we have something in the beginning, and we're subtracting the values and dividing that by time. So it's a pretty simple, straightforward formula. And this is just a measurement, really, of how fast it's going. It's like speed, right? How far did you go, and how long did it take you to get there? That's speed. So this is really like a speed equation or a velocity equation. Okay? So let's do an example problem here. As this balloon rises from 1,000 meters to 2,000 meters, it does so in 5 minutes. So at what rate is it rising? Well, we can do the math, and the first thing you would want to do is figure out what variables are which. What are we subtracting, and what's on the bottom? So time is expressed here in minutes, 5 minutes. These are the two values that we have to subtract. So we're going to subtract 2,000 minus 1,000, and we'll get 1,000 meters, and that's going to be our numerator. And then time is 5 minutes. Okay, and we're just going to divide the two values. So we're going to do 1,000 meters divided by 5 minutes, and that will give us our answer. And the answer is going to be labeled meters over minutes, or meters per minute. And if we do the math, that'll give us an answer of 200 meters per minute. There you go. Okay, so the answer was letter C. So simple, basic math, subtracting two values, dividing by time, that's rate of change. Okay? And you're going to be using this for a lot of different examples. That was just an example of a change of the height of a balloon. Okay? Now, we can express things graphically, and you guys know about line graphs. You've drawn them before, I'm sure, and you're going to be drawing line graphs for my class as well. And I'm not going to go into the details of when and why these are used, but the purpose of this is just to express the fact that we have two different variables, and two different variables can be shown in a relationship like this to be directly related to each other, which we're going to talk about later on. So line graphs are really useful for showing the relationship between these two variables. Okay, but be aware that the bottom here, the x-axis is the independent variable, the y-axis is the dependent variable, and it would be good to know that, and also just understand that there's a relationship here. Okay, this is a typical not graph, but a chart showing you changes in precipitation throughout every month, average precipitation in Syracuse. We could graph this information, and we'd have a really weird looking graph if it was a line graph. It would go up and down, up and down, up and down. A better way to graph this information would be in what's called a bar graph, right, where we're showing the relationships of each month, comparing them to each other. So a bar graph is really useful for measurements and amounts and comparisons of things. So you can kind of see that shown here. These are the months on the x-axis, time, and on the y-axis we have the amount of precipitation, and we can tell pretty quickly which month has the most by just looking at all the bars. So bar graphs are really useful for that purpose, comparing values. Okay. Pie graphs, circle graphs are really good for comparing things to a whole, so it's really good for percentages. This is a graph of the elements in the Earth's crust by mass, and that's actually something that's shown on your reference table as well on the bottom. And you can see the highest percentage, the most abundant element in the Earth's crust is oxygen with 46% and silicon with 28%. And the other ones make up this other tiny percentage here, about 25 or so. Okay, so pie graphs are good for percentages, and we'll deal with those ones too. Now, these notes, if you want to know, if you want to write these down on paper, this would be a good thing to write down on paper, some of this information. If you haven't been taking notes yet, it'd be wise to go back and make sure you write some stuff down. But if you want the actual notes for this, let me show you where it is. Just go to Notes under Class Documents, and there's an actual PDF file here. And if you scroll down to page number 4, you could actually print this out if you want to, and then page 5 as well. And these are the notes here. So I'm going to just present them. If you want to just copy them down word for word, you can do that too. Okay, so graphing relationships. When we're dealing with line graphs, we're often dealing with the relationship between two variables. And often you'll see some type of trend. And you have to know these. These are things that you're going to have to memorize. So a direct relationship. As one variable is increasing, it says that the other one is also increasing. And on a graph, what you would see is something that looks like this, where you have a positive slope, something sloping upward like that. It might have a little bit of a curve to it, but you can see that it's directly related, right? One's going up, the other one's going up. So a good example of this would be planets going around the sun. So if you are farther away from the sun, like the farther out you get, like way out to the realms of Neptune and Pluto and way out there, obviously the distance is really big, and it takes a very long time to revolve around the sun. So there's a direct relationship there, right? When the distance increases away from the sun, the time it takes to go around the sun also increases. So we have a positive or a direct relationship. Okay, so that's a good example. Inverse relationship. This is where you have one variable increasing, but the other one is decreasing. And the graph might look like that. It might have a little bit of a curve, or it might be more straight. But you can see that one thing's going up while the other one's going down. So a good example of this is altitude and temperature in the troposphere. So if you climb a mountain, you notice that it gets colder and colder and colder as you go up in altitude. So the altitude is increasing, but the temperature is decreasing. And so you have a inverse relationship. And that's a good example of one. And there's plenty of other ones out there as well. Okay? Here's one that we kind of talked about at the very beginning. It's called a cyclical relationship. So you have one thing changing or increasing over time. Usually that's time. The other one is changing in what's called a predictable pattern. And the graph is very unique. It goes up and down and up and down and up and down and up and down. So any event that is cyclical is very predictable. So I can make some guesses as to what's going to happen beyond here, right? I know it went up and then it went down and then it went up and then it went down. And I'm guessing that beyond here, if I were to extend this graph, it would probably look like that, right? So I can make a prediction as to when is the next peak of this hill going to be? When in time will that be? Well, I can make some predictions. How far is it from here to here, right? And therefore that same amount will be the distance from here to here, or the amount of time from there to there. Okay, so anything that is cyclical is also very predictable. And there's a lot of things in earth science that are cyclical. Phases of the moon was a good example that we just talked about before. So the full moon might be the peak right here, and then it decreases down to the new moon, and then back to full moon, and then back down to new moon, and so on and so forth. You can see here the changing moon phases throughout a 29.5 day time period. And this is actually back in April, but you can see how it went from full moon, and now it's starting to wane, and it's decreasing in the amount of illumination, and then it gets down all the way back down to nothing, and that's called the new moon. And then it starts to wax and get brighter and brighter and brighter, and you can see that this is a very cyclical, predictable change. Tides, very, very cyclical. Like the water rises and then it falls, and it happens like 4 times every day. So there's lots of cyclical relationships, and I figured I'd give you a few there, okay, to copy down. All right, so with that, there's one more. Let me just erase this, get rid of all of my drawing on here. So the last type of relationship is what we call a static relationship, or a no relationship. There's no relationship between the variables, and we would write that as, sorry, let me go back to this. When one variable is increasing, the other is staying the same. And so you see a nice flat line like this. And there's good examples of this. Well, maybe not a good example, but you can think about like your heartbeat was kind of like this, right? Up, down, up, down, up, down. So it's pumping blood. But when you flatline like this, right? And you hear that beep, 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 and then it goes beep, heart monitor. Not good, right? And they have to get the paddles out and paddle you, right? Not
No, Claire. No. Normal sinus.
The thing that's staying the same is like your heart's not beating. Okay, so one variable is increasing, the other staying the same. And a really good example of this is something that we'll deal with in your, well, we dealt with in your lab, was density. No matter how big or small the object is, if it's made out of the same material, the density stays the same. Okay, so that's a really good static relationship. All right, now in this picture here, you don't have to write this down, but you can see this is relief, so it's kind of like slope and how much erosion happens. The steeper the slope, the more erosion there is. And so you can kind of see this is a scatter plot graph. And within that scatter plot graph, you can kind of see there's a relationship, a trend there. And if we were to draw a good best fit line through all that data, it would probably be a nice linear best fit straight line straight through there. And so we would call that a direct relationship. And we might write that as the relief increases, the average rate of erosion also increases. But you can kind of see this in a scatter plot graph, not a line graph, but you can see the relationship there. Okay, and we'll deal with scatter plot graphs as we go along here. All right, let me do one more here. And you can see on this, this picture here, there is a relationship between 2 variables going on here. There's 2 lines drawn on this. There's relative humidity, the solid line, and air temperature, the dotted line. Now, over time, on the x-axis here, they're going up and down and up and down and up and down and up and down. You can make predictions as to when the temperature will be high again after this, right? We could extend this line out and go this way, okay? Same is true with relative humidity. It would probably go up like this and back down again. So there's good predictability of this graph. The relationship over time is cyclical. However, compared to each other, there's an inverse relationship there. So let me explain. When the temperature goes down, the humidity goes up. And when the humidity goes down, the temperature goes up. And remember, when one thing is increasing and the other one's decreasing, we call that an inverse relationship. So you have to be careful. In this case, when we're talking about the relationship between temperature and humidity, that's inverse, okay? And so we would say, in this case, that when the temperature increases, the humidity decreases. If this was over time, we'd say it's cyclical. So just got to be careful in what you're predicting here and what you're actually interpreting in the data. Okay, so that's pretty much it. If you have any questions about these graphing relationships, that's the most important part about this, those 4 relationships. You need to know them, and I'll just go quickly through them again. Remember, direct, inverse, cyclical, and static. Okay, and that's it.